This is Unit 3 inverses still, and this is Day 5 conjugates. Sorry for the typo here. What we're going to do is actually take a look at the warm-up on this video, because this is something slightly new, is that you can use distributive property with these radical expressions. And what that would look like is I would distribute the negative 2 times 7 root, or negative 2 plus 7 root 10 to both the 5 and to the minus 3 root 2. We'll multiply the negative 2 plus 7 root 10. For those of you that like to think through FOIL, that is the same thing here. First, outer, inner, last. Let's see how this multiplies out. I have negative 10, 5 times negative 2, plus 35 root 10. Then I'm going to distribute the minus 3 root 2, so that's going to be positive 6 root 2 when I multiply it by negative 2. And it will be negative 21 root 20. You'd want to combine anything that you can and simplify anything that I can. As I look through here, nothing can combine, but on the last one, I can reduce the root of 20 by dividing out a 4 from it, so I will do that. So negative 10 plus 35 root 10 plus 6 root 2 minus, this will be 21 times the square root of 4 times 5. Alright, and I will square root that 4 and bring it on out. So my final answer, negative 10 plus 35 root 10 plus 6 root 2. When I square root that 4, it will be a 2, and that 2 will multiply this 21, so it will be minus 42 root 5. This is my final answer because nothing can be combined, adding or subtracting wise. I've multiplied everything I can. I have nothing else that will simplify out. So, there we have it. And it's clearly an irrational number. These three terms themselves alone are irrational. Now, on example 1, I'll go ahead and state from the start, this is actually going to simplify to a more pleasant answer than what our warm-up did. Going ahead and getting that started, distributing this 5 to the 5 and the 3 root 7, I would get 25 plus 15 root 7. And now what I'll do is I'll distribute negative 3 root 7 to both the 5 and the 3 root 7. So I'll get minus 15 root 7 minus 9 root 49 when I multiply the negative 3 root 7 with the positive 3 root 7. 3 times 3 is 9. 7 times 7 is 49 inside the root. The reason why this comes out a lot nicer, the 15 root 7 minus 15 root 7 will cancel each other out to 0 root 7. So they're gone. Now I'm left with 25 minus 9 times the square root of 49. Now square root of 49 itself is 7. No more root. So this is 25 minus 63. Alright, and that is negative 38. So when I had these two expressions multiplying, I actually got a rational answer. What these two expressions are called, they are called conjugates. We're going to take notes on those now. As you can see, this example 1 shows what happens when conjugate pairs are multiplied together. The answer is rational. So that is actually the definition of what makes something conjugates. A pair of irrational or imaginary numbers are conjugates if their product results in a rational number. Examples. Irrational numbers that multiply to a rational number would be the square root of 2 and the negative square root of 2. That's a conjugate pair. If I multiply those together, I would get negative 2 as my answer, which is rational. And anything that follows the form where the root has a different sign. So if I have something like 5 minus the 3 root 7, the conjugate pair would be 5 plus 3 root 7. And if we had something like 17 plus the square root of 10, its conjugate pair would be 17 minus the square root of 10. So I think that kind of gives you enough. And the reason why these are conjugate pairs, They are from, if you look at quadratic formula, the plus or minus the square root inside there, the quadratic formula always results in conjugate pairs. So keep that in mind as we move forward, that's where it's coming from. Now, as far as imaginary ones go, these are going to be called specifically complex conjugates. And there, anytime that you see, excuse me for misspelling that, anytime that you see something like A plus BI, its complex conjugate would be A minus BI. So something like 5 minus 2I, its complex conjugate is 5 plus 2I. Things like that. If ever you have just like a regular old I, its complex conjugate would be negative I. We don't apply conjugates, though, to rational numbers. Like 5, well, there is no conjugate to 5 because it's already rational. One last example of complex conjugates, you could have something like 7 plus I. Its complex conjugate would be 7 minus I, changing the imaginary part's sign. And again, this is from the plus or minus the square root inside the quadratic formula. Alright, now you're going to actually see where these complex conjugates and conjugates in general are used. So this would be a situation here where you'd have the square root of 6 on the denominator. That's just no good. It is not simplified. But if I multiply by the square root of 6 over the square root of 6, the problem with that is I would end up with 3 root 6 plus some other terms. I wouldn't actually be canceling it out. Anytime there's addition or subtraction, you need to use a conjugate when you're rationalizing the denominator. So the conjugate I'm going to use here is 3 minus 2 root 6. I will multiply that conjugate to the numerator and denominator. And when I do that, the numerator would now be 15 minus 10 root 6. I distributed the 5 there. Down here on the denominator, I'm going to distribute the 3 here, so 3 times 3 is 9. 3 times negative 2 root 6 is negative 6 root 6. 2 root 6 times 3 is 6 root 6. And 2 root 6 times negative 2 root 6 is minus 4 root 36. And now everything's going to start canceling out in the denominator. These middle parts cancel. And in fact, what you're going to see me do is when I multiply with conjugates, I'm going to use the rule that it's a difference of 2 squares. A squared minus b squared is what the answer is going to end up being. Now in the numerator, I still have 15 minus 10 root 6. There's no simplifying to do there. On the denominator, I have 9 minus 4 times 6 is what that changes to. And the 4 times 6 gives me a 24. So I got 15 minus 10 root 6 over 9 minus 24. And 9 minus 24, I can get to negative 15. You can see where, since that denominator came out as a negative, I actually put that up on the side of the fraction, that I can negate the numerator, actually. In this kind of situation, you would want to divide out a 5 from each of the terms, so I'd have a 3 minus 2 root 6 over 3, and that was because the 15, 10, and the 15 could all be divided by 5. So, oh, and don't forget my negative here. That would be one way to write my answer, or I could actually distribute that negative to the numerator, so it'd be negative 3 plus 2 root 6 over 3. You just wouldn't want to leave that negative on the denominator. It's not nice to leave it down there. One of these two answers is the answer. Alright, with this situation, we do have a radical in the denominator again, and since it's addition or subtraction, we're going to use a conjugate. You don't have to change the sign of the part that's actually being square rooted. You can just change this sign here between them and be okay. So you'll see what that plays out as. So I'm actually going to multiply this by x to the half minus 3 is what I'm going to use. And I'll do that to the numerator and denominator. Going to be quite a bit of multiplication right here, but it's going to be alright. So the numerator, when I distribute out the x, I get x times x to the half is x to the 3 halves. Remember to add your exponents. X to the 1 plus 1 half, that's 3 halves. Then distribute the x to the negative 3, so minus 3x. I'll go back and distribute the 1. That's easy. Plus 1x to the half minus 3. There's my numerator. I'm not going to be able to do anything else with my numerator. That's going to be it. On the denominator, remember, I'm going to use the difference of two squares. It's going to be a squared minus b squared. So if I square a, I get x to the first power. That's x to the half times x to the half is x to the first power. Now 3 times negative 3 minus 9, a squared minus b squared. As I look here, there are no common factors that will factor out of this. We'll get later where there is with these rational expressions, but there's not right now, and we're done. Now, if you thought that all that was fun, now we get to use a complex conjugate on the same process. Yay! Alright, let's go ahead and get this knocked out of the park. The complex conjugate I'm going to use here is 2 plus 3i. And yeah, that's the easy part of this, is figuring out what the conjugate is. You just change the sign in the middle. On the numerator here, I'm going to get a 10 plus 15i from distributing the 5. Now on the denominator, remember, a squared minus b squared. My a is 2, so that squared is 4. Minus b squared. My b is 3i. When I square that, I get 9i squared. Alright, that right there is the issue. You do not want to leave that as I squared. The only I should ever get in the answer is I to the first power. The rest of them, I to the second, I to the third, I to the fourth, you can reduce down to something. So right here, I to the second can be rewritten as a negative 1. Think about it. If you remember that I is equal to the root of negative 1, then that means if I square that up, the square and the square root would cancel out. So I squared would be negative 1. So that's what I'm going to do over here, is I'm going to replace that I squared with a negative 1. Numerator again. Nothing's going to happen on the numerator, so let's just leave it as 10 plus 15i. On the denominator, though, that 4 minus 9i squared is going to become 4 plus 9 because I squared was negative 1. And 4 plus 9 is 13. Alright, that's my final answer. No common factors to divide out. Now, if you thought all this was fun, just wait until we write equations with conjugates, which is coming up now. Alright, this will look like a lot of fun. Write a polynomial equation in standard form that has the root 3 minus root 2. Well, if it has that root, 3 minus root 2, think back to quadratic formula. It would have to have the root 3 plus root 2 as well. So this is going to be a quadratic since there's 2 roots. So what I'm going to do really quick is state the obvious one, x equals 3 minus root 2, but I'm going to state another one, that x equals 3 plus the square root of 2. And what we're going to do is we're going to actually be able to write a polynomial equation with those 2 roots. Because if one is a root, its complex pair has to be a root. Alright, get these equal to 0. Remember, we're figuring out what our factors are at the moment. So this factor would be x minus 3 plus the root of 2 to get it equal to 0. I subtracted 3 and I added root 2 over. Over here I'll subtract the 3 and I will subtract root 2. So x minus 3 minus root 2 is my other factor. And what do factors do together but multiply? So x minus 3 plus the root of 2 times x minus 3 minus the root of 2 are going to multiply together, and this will give us our equation. Now we will distribute all this out, and it looks like fun. Yeah, wait, no, the other thing, pain. Alright, so I'm going to distribute this x to all 3 terms right now. That's going to be x squared minus 3x minus x root 2. Now I'm going to go back and distribute negative 3 to all 3 of these. So I'm going to have minus 3x plus 9 minus 3, or excuse me, this would be plus 3 root 2. And now I'm going to go back and distribute the root of 2 to all 3. So I'm going to have positive x root 2. I'm going to have minus 3 root 2. And I'm going to have minus the root of 4. And while this looks absolutely just bad, good things start to happen really quickly. Like, for instance, the minus x root 2 right here and the plus x root 2 cancel. The plus 3 root 2 cancels with the minus 3 root 2. I have some things that can combine. Nothing combines with x squared, but a minus 3x and a minus 3x makes minus 6x. I'll still have a plus 9. Oh, and this last one here, this minus root 4. The square root of 4 is 2, so it's minus 2. And then I have my answer would be x squared minus 6x plus 7. And that is a polynomial in standard form with the roots 3 minus root 2, and by default 3 plus root 2 would also be a root of that equation. Wasn't that fun? But wait, there's more. Could you do it for complex numbers as well? Yes, you can. I'm glad you thought of that. So, if x needs to equal 4 plus 2i, then x would also have to equal 4 minus 2i. That's how conjugates work. So my factors here, over here on the left, is x minus 4 minus 2i. And my factor over here on the right, by subtracting the 4 and adding the 2i, would be x minus 4 plus 2i. And then we'll go ahead and multiply those factors, because that's what factors do. And when we do that, it's going to look just as bad as the last problem, but then it's going to work out pretty well. I'm going to distribute this x to all three, so I have x squared minus 4x plus 2ix. Looks like a b still, cancel out in a minute. Distribute the negative 4 over to here. Minus 4x plus 16 minus 8i. And now I'm going to distribute the negative 2i out. So I'm going to have minus 2ix plus 8i and minus 4i squared. And as bad as that looks, recognize things that will cancel out. Plus 2ix minus 2ix cancels. Minus 8i plus 8i cancels. And it's that pattern every single time if you're doing it the same way every single time. But don't leap through your steps. You actually want to write everything out. Here we go. I've got x squared. If I do minus 4x, that's minus 8x. I still have this plus 16 right here. Now down here at the end, minus 4i squared. Remember, replace I squared with negative 1, please. And this will be x squared minus 8x plus 16 plus 4 when I multiply that. And I'll have x squared minus 8x plus 20. And this is my final answer. This is the equation that would have the root 4 plus 2i, and it is in standard form. Thank you very much.